Well, this is John Black, Super Chemist. We're here this time to talk about the Octet Rule. Just because it says octet doesn't necessarily mean that everything it has to do with 8. Okay, but it's a good general rule. A rule that says that the most stable electron configuration for any atom is when the outermost shell is full or empty. I know a lot of people they ain't gonna like me saying or empty. It might be incorrect to say, so I'm just bringing it up so you know. But I like to think of it as full or empty. It's take it or leave it. That's how atoms are. They take it or leave it. They want it all or nothing. So the outermost shell. What is a shell again? A shell is just a floor number. If you're on floor 1, you're on shell 1. If you're on floor 2, you're on shell 2. It's just a certain amount of distance that you're away from the nucleus. The higher number shell or the higher number floor means that you're further away from the nucleus. And what are valence electrons? That was our last video. They're electrons that are in the most outer shell, so that they're furthest away from the nucleus. Okay. Now this octet rule deals with the outermost shell, and these valence electrons are in the most outer most shell. So they're going to be together here. Okay, they're related. Now remember how we said the left and right were the horizontal columns. Those coincide with your shells. Like this is period 1, period 2, period 3, but it's also shell 1, shell 2, and shell 3. Until you get down to the d orbitals, it's pretty much that way. And remember that columns that go vertical up and down, those tell you how many valence electrons your atom has. Okay. Now, when you have an octet rule, we're talking about and valence electrons. We're always talking about that last shell that's being filled or unfilled. Okay. For helium and hydrogen, they only have one shell. See right here? So if they want it filled up, they can only put 2 in their shell, right? 1, 2. And then this shell is filled up. See, that's why they didn't put helium over here where it belongs, because it has a filled outer shell. Okay? And that means that it is the most stable electron configuration there is. There are noble gases over here because they don't react. They already have their 8 electrons, their 8 valence electrons. And well, in this case, 2. Just so happens that most of the ones that you deal with have 8. You know what I mean? Like this next row, right? Shell 2, period 2. It has 1, 2, and 6 over here is 8 electrons. And then its outer shell is filled, right? So it would want 8 to be a noble gas. All these hydrogen wants to be a noble gas like helium, lithium and beryllium want to be a noble gas like neon, and they all want to move over to the right where the electron configuration is perfect. Now this one right here, this one can actually have 8 or 18. Because remember your d orbitals, this is actually a 3d orbital, right? So if you're in this aisle, right, this shell 3, period 3, you have 8 electrons for your valence electrons. But you could also have, if you filled up all your D's, you could also have 18 in your shell 3. You know what I mean? And as you go down, then you got your f orbitals, and there are different exceptions to the rule. But I'm not going to get into all that. The important thing is that you need to understand that when you have a full shell, then you are the greatest. You are so stable it's unreal. And when I say that you can lose a shell, because if you think about it, look at sodium. It has 1 valence electron. If it loses that electron, it would go back to neon electron configuration, right? And that's what it wants. It wants to be any noble gas, really. It doesn't have its 3rd shell filled, but if you remove that 1 electron, now the shell 2 is filled and the shell 3 is totally empty, and that's the way they like it. It's all or nothing. But for the hydrogen, it only has 2 in its shell, so it can only fill up 2. Now I'm actually going to talk about some chemical reactions, believe it or not. Binary salts, meaning you have 2 sides to the salt, 2 parts to the salt, binary. I want you to think about it. Now these first rows have 1 electron, 2 electrons, and we're going to skip over the D's, okay? This has 3, 4, 5, 6, 7, and the magic number 8 electrons for the octet rule, okay? So these are numbered too by group. Group 1, 2, 3, 4, 5, 6, 7, 8. If you can add 2 numbers together to equal 8, this should be easy, okay? Like 7 and 1 make 8, right? 6 and 2 make 8. 5 and 3 make 8. And the reason why I'm saying that is because if you have a binary salt, we're talking about a metal and a non-metal. You got something over here that has a little bit of electrons, and you have stuff over here that has a lot of electrons, okay? Well, let's say you take this number 1 ow, and you take the number 7 ow, and this guy gives this guy an electron. Now he has 8 electrons. He only needed 1 more, right? And this guy, he gave it away, so he moves back down to the block before. Let's say it was potassium. He'd move back down to here, and he has a full outer shell. It's not his full outer shell, but it's still, you know, his is empty. But it's all or nothing. He's got an empty and a full one, so he's happy. If he was with chlorine, chlorine can hog that electron, and it would have a full octet. You know what I mean? It would be at the argon electron configuration. Now, look at this. This is group 2, and this is group 6. What does 6 and 2 equal? The magic number 8. So beryllium could go with oxygen, and you would have they would both get their octet. Okay, now this is just going for binary, simple, you know, one-on-one. You got a positive, you got a negative. All they're doing is either sharing or almost giving away the electron. The thing is they have to add up to 8. That's the most, or not 8. It could be any, it just got to add up to be over here where the shell above it is totally empty and the shell that it's in is totally full. You know what I mean? Alright, I basically copied the first 3 rows of the periodical chart. You can see hydrogen, helium, lithium, beryllium, so on. I took out the D orbital metals, so it's nice and simple for you, you know what I mean? You just got your S and your P's. Every time you move down a row, you're moving to a new shell, I want you to notice, remember, the columns 1, 2, 3, 4, 5, that's just telling you how many electrons you got. Column 5 has 5 valence electrons. Now I want you to look at how I put a dot. See, these are my electrons. First row, see how they all have 1 electron? Second row, all have 2 electrons. Third group has 3 electrons. Fourth group has 4. Now if they want 8, these guys over here, they only need 1. This guy only needs 2. This guy only needs 3. They're obviously going to try to get a couple more electrons. It'd be a lot easier for fluorine to get 1 electron than it would be to give away 7. I mean, giving away 7, that's crazy talk. And over here, on this side, on the left, they don't have any electrons. Instead of them trying to fill up their orbital, it would probably be easier, especially these guys, to empty their shell. You know what I mean? This lithium, if he gives up that 1 electron, he could have go to the previous shell and have that filled up. You know what I mean? So obviously the ones on the left are going to try to give away their electrons. Okay, that's why they're called reducers. So they're giving electrons away. Electrons are negative. That's like a bill. If someone gives you a bill, then you've been reduced. Your bank account's reduced. And this side, is considered oxidation because oxygen's there. That's how I always remember it. And a lot of people get oxidation confused because it's about electrons, okay? And I don't think they get that a lot of times. You know, why is this oxidized? Because it takes electrons, okay? So it's not screwing you, it's oxidizing you. But anyways, that's for a later video. What I want you to notice is that these electrons, the way I have them, I think that's called an Lewis dot structure. I'm not 100%, but it's irrelevant. This is what you should get used to writing your atoms like. The letters that represent it, and then the electrons go around it. And I want you to look over here. It's just like a street sign, okay? See how down there I got the electrons? It's just like a four-way. It's like there are cars here, cars there, and they're all at a four-way. That's how it is. You got two on the left, two on the right, and two on the top and two on the bottom, just like a four-way. And that way you can kind of put these in together like puzzles. Like look at this fluorine and this hydrogen. He needs one, he needs to get rid of one. Look when you put them together, it's like a puzzle. This slides right in there. Same with lithium carbonate. It just slides. See how it just slides right in there. And if you look, once they become an item together, once they become a binary salt or whatever, one of them always is surrounded by electrons and one of them isn't. Okay? And that's why I say they either want to fill their outermost shell or empty it. Okay? People don't like to hear that empty part. But it's true because of hydrogen. Even if they don't like me saying it on this, you got to say it about hydrogen. When hydrogen gives up an electron, it's giving up, it's totally emptying out its orbital, or its outer shell. So I like to think of it as the chlorine has, he's got his octet filled, and this guy, or his outermost shell filled, and this guy has his outermost shell empty. But it's up to you on how you want to think. Now, look at this one. This guy has two. He's in a nextile. So guess what? Now they move over to one exile. If you're going to add an electron here, you're going to have to take one away over here for it to still equal 8, right? But I want you to see, look at how it's like a puzzle. It just slides right in there. Now check out magnesium. It has 2 electrons. See how, so you're going to have to move over. You know, if you move over this way, then this way has to be moved over until you meet in the middle where it's 4 and 4, like carbon and carbon. But you can see how it's just like a puzzle. Look how it just slides right in there to form the magnesium oxide, just like a puzzle. You can see the oxygen looks like he has his outer shell filled, and the magnesium looks like he has his outer shell empty. But do you see how each of them has they're either filled or they're empty? They're never in between. They can be in between, but then they're not the stablest electron configuration they could have. And that's basically what the whole octet rule is. It's filling in your most outer shell or emptying your most outer shell. You want all or nothing. You don't want nothing in between, teeter and totter and you around, you know, shifting you left and right. You want a nice straight path, narrow way to go. It's either all or none. So keep in mind, we're almost done with this. Basically, all these videos I've done so far are all about the periodical table. And as soon as I can stop thinking of things that the periodical table tells you to help you as a tool to synthesize chemicals, then I will stop these videos about them. But I think there's only like maybe 2 more videos. Then I can do the playlist for that and move on to something better. So I know this is kind of boring, but it is starting to get into actual thinking about how you get 2 atoms together and put them together as a compound. Anyways, I hope you have a great day, and always remember, science is great.